So, good afternoon, everybody. Uh, in the last class, we discussed about the defects in the material, okay? And then we concentrated mostly on the thermodynamically. First of all, why are defects important? Then thermodynamically generated defects, and then we also talked about what is the classification of defect based upon the dimensionality. So picking up the threads from there. All right. So starting again, classification of defects based on dimensions. Okay. So as the name suggests, this particular classification use the dimensionality of the defect to classify them into various classes. Okay. So first one is zero dimensional defect that we have already studied about. The defects that occupy one lattice side. So they could be your vacancies, interstitial, Schottky, Frenkel, and also the color center. Then you have one-dimensional defect, and as the name suggests, these are the defects along the lines. And they're also called as dislocations. And two basic type of dislocations are edge dislocation and screw dislocation. Then the defect that span over an area, okay, that is over two dimension are called two-dimensional defect or also the surface defects. So some of them are grain boundaries, then twist boundary, tilt boundary, twin boundary, stacking fault. We'll talk about them a few moments later. And then of course, we have three-dimensional defect also called as volume defect, and these occupy a three-dimensional area or the volume in the material. So these are like pores or cracks and also the bubbles. Okay. So talking of 0D defect, we have already talked about, so we'll not talk about them again. 1D defects, okay, as the name suggests, the defects that are in one dimension. And we can also call them as point defects that are arranged in a line because that also becomes one dimensional. Now they are important because they affect the mechanical, electronic, and photonic properties of the material. And one very important thing which should be mentioned here, what makes it different from the 0D defect are the zero dimensional defect are the thermodynamically generated defect, at least the ones that we studied. That is your vacancy, interstitial, Schottky, and Frenkel. They are all generated due to thermodynamically imparted stability on the material. But line dislocations or the line defects, they are not thermodynamically generated defects. They are formed by some sort of deformation during the solidification or during the synthesis or during the crystallization. When the material is deformed, these line defects, they creep into the material. Okay. And because they are not thermodynamically generated, they raise the energy of the system. So one dimensional defect, repeating it, unlike 0D defects, are not thermodynamically stabilized defects. Now there are, as I just mentioned, there are two basic types of one dimensional defect called the edge dislocation and screw dislocation. And then most of the time, the dislocation that you observe in a material can also be qualified as a combination of these two. But let us do the simplest cases and let us see what these are. Okay. Edge dislocation occurs if you imagine a pure crystal when there is a plane of the atoms that starts from the beginning, but it part midways. It just stops midways abruptly. It is associated with the edge dislocation. Just to give you an example, just to make it more visualizable for you people, imagine this is your perfect crystal, okay? So you can see that it has, you can imagine it as, of course, as I said, plane, lattice planes or planes are basically the imaginary entities that we use to visualize the or describe the crystal structure. Now, let's say this cube, you can imagine it as the plane of like parallel planes in this direction, okay? Now, suppose a plane, let's say this one, it started from the top, but it parted midways, and then it did not exist below that. Something like this will appear. So you have other planes, but this particular plane started from the top, but it parted midways, and there is an absence of this particular plane below this line. This line that is going inside the surface of the cube, okay, that represents the incomplete plane is called edge dislocation. Okay, I'll repeat again. Suppose you have this plane which started from the top, but it finished abruptly somewhere in the middle. It is not being continued in the later half of this crystal. What will happen is that dangling edge across, which shows the incompleteness, which shows the ending of this plane, is your edge dislocation. So edge dislocation in this particular case is perpendicular to this surface. All right. Why this is associated with high energy and not thermodynamically stable? If you just concentrate at this edge, which is going inside this plane or the edge dislocation, because once this plane ends abruptly, all the bonds above this particular line will actually be compressed together, and the ones that are below this particular line will be in the state of slight expansion. Okay, and we know that whenever your the interatomic distance is either lesser than the equilibrium distance or more than the equilibrium distance, the energy of the system increases. Okay, so that is why edge dislocations or dislocations in general are associated with high energy. This diagram below shows the same thing that you have seen here in terms of the layer of atom. So this is basically the layer of atom that represents this front face of the top figure. Okay, so you see that all of them are nicely arranged in two dimension here rather. Now what happens is, when this particular plane of atom, it parts midways. Now this line that goes inside at this particular point is your edge dislocation. Another way to visualize this, you look at this. Okay, so what happens is, you have this cube. Okay, now imagine that you have divided this cube into two halves along this plane A, B, C and D. All right, now you put your hand on the top surface of this cube and try to push it in this direction, keeping in mind that you are that whatever movement happens, it does not go beyond this line. So what will happen is, this top plane, okay, will go and combine with the plane line here this way. Okay, that the bonds will be formed here and this plane will be now half. Similarly, the second plane will combine with the second plane here will combine with the third plane at the bottom. The third here will combine with the fourth plane at the bottom till you reach this line. So situation like this will appear. Okay, your front plane will combine with the second at the bottom, second with the third, third with the fourth, and so on till you reach this line. Now, this particular plane does not really move. So, what happens is, this particular line of atom will not have a counterpart in the bottom part of this cube. So, it will be dangling halfway. Okay. And this line EF is called edge dislocation. All right. So now this, but the just telling you about some nomenclatures here. The plane A, B, C, and D, in which all this thing is happening, is called the slip plane. The part A, B, F, E is called the slipped part of the plane. The part E, F, C, D is called the unslipped part of the plane. And the edge dislocations are represented by either edge dislocations are represented by this or this symbolically, sorry, this or this symbolically, depending on whether the plane started from top and then parted midways or it started from bottom and then parted midways. All right. I will again repeat this, all of this in the very, I'll try to summarize this. So edge dislocation happens when there is a plane of atom that part midways. Because it part midways, it does not have that particular line which is parting, it does not have a counterpart in the bottom part of the crystal. And that line which is held dangling is called edge dislocation. Edge dislocations are represented by either this or this, depending on whether your plane started from the top and parted with midways, or it started from the bottom and then it ended abruptly. Okay, so this is all about edge dislocation. Now, how do we quantify the dislocations? There has to be some way to quantify it, right? If I say my material has got edge dislocation, then what is the magnitude of that edge dislocation? So that is defined by a quantity that is called Berger's vector. Okay, it is represented in terms of the atomic distances. So basically what is Berger's vector is? It is the measure of the lattice distortion that is caused as the consequence of existence of your line defect. What is it? Repeating it again. It is a measure of the lattice distortion that is caused by the presence of the line defect. Okay. Just to make it more visualizable, you imagine, you look at this particular figure. Again, this is the plane of atom that is on the front of your cube, right? And I define a random rectangle in this particular, on this particular face of the cube, which is represented by the solid lines here. And let me start from the point P, okay? So you see that if it is a perfectly well crystalline material without any dislocation, what will happen is, let's say I move 5 interatomic distance in the towards top, I end here. I move 5 interatomic distance in the right direction, I enter here. I move another 5 interatomic distance in the bottom direction, I end up here. And I again move 5 interatomic distance and I end up at my original point P. Now let us try doing that in this figure on the right hand side, which now has edge dislocation. What will happen is, you start from P, move 5 interatomic distance towards top, towards right, towards bottom, towards left. What will happen is, you will now not end at point P, but you will rather end at point Q. Now, the amount of distance or the magnitude of distance that you need to travel to go back to the original point P, that is called the Berger's vector. Okay, so here the distance QP is your Berger's vector. Repeating it again, the amount of distance that you need to travel to go back to your original point P is your Berger's vector. In this case, the distance QP is your Berger's vector. It is denote, now since it is a vector, it has to have a direction also. Okay, so in this case, the Berger's vector, no, not in this case, Berger's vector is denoted by small letter B. And in this case, its direction in case of edge dislocation is perpendicular to the edge dislocation. Your edge dislocation at this point goes into the plane of paper and your Berger's vector is in this direction. Okay. So Berger's vector for an edge dislocation is perpendicular to the edge dislocation. And the closed path that we have adopted across the edge dislocation, this closed circuit that we have adopted across the edge dislocation is called the Berger's circuit. Okay, just some nomenclature for you to understand later. Let's say you are studying about the dislocation or defect sometime in some context. If these are the words you come across, you should know what they mean. And of course, they would have application and there are further details about them, but that would depend upon what you are doing at that moment. And then you can go deep and study more about them. So this is just the introduction of what edge dislocation is. Now coming to screw dislocation. This is a little bit more difficult than edge dislocation to understand. So what happens is, I will not read whatever is written here. You just concentrate on this particular cube. This is your perfect cube without any dislocation. Okay. Now you imagine that again you have bisected this cube, let's say in two halves across plane A, B, C, D. Okay. Now what you do is you try to dissect it again in the YZ plane. This was the XY plane, ABCD. Now YZ plane that goes from here to here. Okay. So what happens is, let's say this is only for your ease. Nothing is getting bisected or something. This is just to make you understand how the dislocation would appear. Let's say I have this area now here. Okay. After dividing it first in the XY plane and then is this direction. Now you put your hand on this particular area and then try to move, apply the pressure from right hand side to the left hand side in this direction. Okay. Considering making sure that this part at the back, this remains at its own point. Okay. If you have done this operation, this is how your tube will look like. The front half of the top half has moved forward. The back half of the top half is still there. Okay. And then the bottom is of course not affected. So what will happen is, what you have created is in all this scenario, can you see this particular path over here? Now that path has now become this. So what you have done is you have actually created a step here, this thing. Okay. Now this line EF that is passing this particular line EF, this is now your across near to which the step is created is your screw dislocation. Now, why is it called a screw dislocation? Okay, that's a funny word to terminology, but there is a logic behind it. You concentrated this figure. Okay, now your atom, if you concentrate here, your atom 3, 7, 11, and 15. Concentrate on this figure. We'll go very slow. Your atom 3, 7, 11 and 15 are actually in the back half of your top half, and atom 4, 8, 12 and 16 are in the front half. Similarly, atom 1, 5, 9 and 13 are in the front half, and atom 2, 6, 10 and 14 are in the back half. Okay. Now, when you did this operation, that you tried to push the front half of the top half from right hand side to left hand side, what did you do? Your atom was earlier going very nicely as 1, 2, 1 was joined to 2, 2 was joined to 3, 3 was joined to 4, and 4 was again joined to 1. Similarly, 5, 6, 7, 8 and 8 was joined to 5. But when you did that operation, what did you do? 1 is joined to 2, 2 is joined to 3, 3 is still joined to 4, but now your 4 is joined to 5. Okay. 5 to 6, 6 to 7, 7 to 8, same as before applying pressure, but now after applying pressure, 8 is joined to 9. Similarly, 9, 10, 11, 12, same as previous, but 12 rather than being joined to 9 is now joined to 13. So if you try to concentrate on it, what you have created is like, do you know a screw? The screw has got those rings over it which go around the screw, or like we have got those helical staircase where a rod goes in the center and the stairs revolve around that. Stairs actually move like a rings, like it is in a screwdriver. So because of the nature of this, that it goes like this, it is called a screw dislocation. So this particular dotted line is your screw dislocation, which corresponds to line EF over here. Okay. Now, what is the Burgers? How do we quantify this? Again, by the magnitude and direction of the Burgers vector. So, if in my perfect cube without any dislocation, I could trace a nice Burgers circuit shown here in the red. But now, when I have created a dislocation and consequently a step, I will have to travel an extra distance to complete the loop. This extra distance here is my Burgers vector and its direction now. Now this is your screw dislocation EF, and the Burgers vector also you see is in the similar direction. So in case of screw dislocation, Burgers vector is parallel to the dislocation line. In case of edge dislocation, Burgers vector is perpendicular to the dislocation line. That is the difference. Okay. So this is about screw dislocation. And how can the dislocation move? These dislocations are very important for the mechanical properties of the material. Sometimes we want them to move to get more ductility. Sometimes we want them to be arrested. And those kind of operations are then done so that the dislocations cannot move. So they are very important for the mechanical behavior of the material. But how can actually these dislocations move? By applying stress or by increasing temperature. And how does it do that? See, suppose you imagine this your crystal and this is your edge dislocation. This plane is parting half phase. Okay. Suppose you apply pressure in a shear stress in this direction on the top of this crystal. What will happen is it will go and combine with this. Okay. Then what will happen? This will combine with this, and let's say then this is left half. So the dislocation has now moved from this position to this position. Similarly, I apply more shear stress in this direction. It will keep on moving. Now it has moved from this position to this position. And then it will ultimately move out of the crystal. This is the example of how we can make the dislocation move by applying the stress. So how we can make the dislocation move by applying high temperature? When you apply high temperature, the thermal energy increases. They vibrate with the higher magnitude. So the thermal energy will make them move out of the crystal in the manner similar as applying stress. But there is also another way. Okay, how can the dislocation be annihilated? They can be removed. Suppose you are applying the stress or you are increasing the temperature and the dislocation are moving, and somewhere close by you have an edge dislocation in this direction, and just below you have an edge dislocation in this direction. That is, there was a plane that started from the top and parted midways, and there was a plane that started from the bottom and parted midways. Now you are applying stress in this direction and they are moving towards each other. Ultimately, a situation might come that both of these half plane will combine, thus annihilating the dislocation. Okay. Dislocation can also interact with your point imperfection or the zero dimensional defect. And how can it do that? Suppose you have an interstitial. Okay. And as we talked about it, suppose this is the edge dislocation that I'm talking about. The atoms above this dislocation are in the state of compression. They're closer. Below, they are in the state of expansion. That is, they are far apart as to what is expected of them based on the equilibrium distance. Now, suppose I have an interstitial. That interstitial would prefer to come and stay in this region where the atoms are slightly farther apart. And this will bring the energy of the dislocation down, making it more stable. So defects can interact. This is just there are hundreds of ways in which defects can interact with each other. These are just two examples how the dislocations can interact with other dislocation, or how a dislocation can interact with a point defect. Okay. Now I'll just take a minute's break here and then we will start the two-dimensional or interfacial defects. Okay, like in case of line defect, they are the one-dimensional defect as they are spread across a line or in one dimension. 2D defects are spread across a surface area, and the region of this surface area is about few atomic distances. Also, like one-dimensional defect, your 2D defects are also not thermodynamically stable, but they are metastable or unstable in nature. And there are different kinds of 2D defects, and let's talk about them one by one. First of all, the surface of the crystal itself is a 2D defect. Why is it? Because let's say I'm talking of a cubic close packing, okay? And we talked about it that in cubic close packing, every atom is surrounded by 12 neighbors. The coordination number is 12. But the atoms that are lying on the surface, they do not have their coordination number of 12 completed because there is no layer of atom on the top. So there are broken bonds, and we know that the broken bonds are associated with high energy. And it is obviously a defect because now your periodicity is being curtailed. So what I want to say here that state here is that the surface of the crystal itself is an example of two-dimensional defect because of the bonds that are not satisfied. Uh, the most important 2D defect that I would talk about, I would say, is grain boundary. What is a grain boundary? You know, many of your materials are basically not single crystal, right? Suppose right now you are looking at a block of iron or a key in your hand, or anything that, let's say, an iron slab. So ultimately, they are all polycrystalline. What do we mean by the word polycrystalline? Polycrystalline means that that particular material has got crystallite, the grains of the same composition and same structure, but they are not single crystal. Many small single crystals or crystallite, they are separated by grain boundaries. So grain boundaries are less crystalline or non-crystalline region that separate two grains in a polycrystalline material. Okay, that is pictorially shown here. These are the regions of your grains where you see the three-dimensional periodicity, and these are separated by these blue lines, and these blue lines are the grain boundary. So basically, the composition of this grain and this grain or this grain or this grain is similar. Their crystal structure is similar, just that they are oriented differently from each other by some angle. Okay, so the region separating them is called the grain boundary. And why do the grain boundary happen? How are they formed? Okay, imagine you are growing a crystal from the melt. What will happen is, as a crystallization start, what is the first process? Nucleation happen. So in different region of the melt, small nuclei will form. And then these nuclei, when the growth happen, these nuclei will attract the atom from the melt towards each other. Okay. And they will keep on growing. Now, at some point, a situation will happen that when different nuclei are attracting the atoms towards themselves, at some point the atoms might feel equal and opposite forces from two different nuclei. Okay, then what will happen? Those atoms will neither be able to go to nuclei A nor be able to go to nuclei B. And then they will settle down there, and there the crystalline structure will not be same as what was growing along with that nucleus, and they form what we call the grain boundary. Okay, again this shows the grain boundary, and you can also see that there is some interatomic distance between atom in these grains which are equal, but here the equilibrium distance between the atoms is more than what you see in the crystalline grain. Now this is a real electron SEM image or a scanning electron microscopic image of the grains and grain boundary in the stainless steel sample. This is how generally the situation looks. Okay. Now, what are tilt and twist boundary? I'll rather first tell you about high angle and low angle boundaries. Okay. We just talked about that different grains separated by grain boundaries have got same composition and same crystal structure. Just that they are oriented at some angle. Okay. So, grain boundaries are classified as high angle or low angle grain boundaries. So what is high angle and low angle? It is defined by extent of the misorientation of the two grains that they are separating. So by convention, low angle grain boundaries are those where the misorientation is less than about 11 degrees, and high angle grain boundaries are those where misorientation is greater than about 11 degrees. So I'll just show you what I mean when I say this. Let's say this is these are your grains, okay? And I'm talking of the grain boundaries here, okay? Now, let's say this is the row of atom that I'm talking about. So if I draw a line across it, okay, but then I also try to see where does the similar line of atom goes in here. In this particular grain, it goes like this. So the angle between these two shows the orientation of these two grain that I'm talking about, grain 1 and grain 2. Okay. Similarly, here, if I draw a line in this direction, and I also try to draw a line along the orientation of atom in this grain, this is the angle. As we see, so this one is called the high angle grain boundary. Okay. And this one is called this is the high angle grain boundary, and this is called the low angle grain boundary. So that is the angle of misalignment of two grains defines whether the grain boundary can be classified as high angle or low angle. And what is an interface boundary? Very simple. When the two grains that your boundary is separating belong to two different composition and structure, then your boundary is called the interface boundary. Because now the two grains are different. They have different composition, or they have different structure, or they have both different composition and different structure. So your boundary is separating two different phases. And easy nomenclature, they are called interface boundaries. Okay. Now coming to what is tilt and twist boundary. They are also grain boundaries. The only difference is when this grain boundary can be represented represented in terms of two or more edge dislocation. We call them tilt boundary. And when the grain boundary can be represented in terms of two or more screw dislocation. Just to make it more clear, let's say I'm talking of a grain boundary here. Okay, this is the grain boundary. I don't want to make a red color over here, but it somewhere goes, starts from here and ends here. So if you see, it can actually be represented in terms of three edge dislocation. One this, other this, and third one this. It can define my region of grain boundary. So this is called a, now these are edge dislocation. So this is called a tilt boundary. Okay. Similarly, if a grain boundary can be expressed in terms of two or more screw dislocation, that would be called a twist boundary. Okay, I hope it makes it clear. You don't really need to go more deeper in it unless you are a metallurgist or you would want to do those kind of material science. Just an SEM, this is not, whatever we were doing was a representation. This is a proper SEM in cubic zirconia, okay, showing the low angle grain boundary. So can you see it here? The grain boundary actually goes this way. So this separates the two orientation, and because they are misoriented by only a very small angle, it's a low angle grain boundary. Okay, twin boundary. Now, this is very interesting. Twin boundary, as the name suggests, occur in couples, occur in pairs. It does not occur in a single boundary. Now, what happens is, it is a 2D defect across which the structure is a mirror image. So what happens is, this is my structure. If I have a twin boundary here, now this is the orientation of the atom. Across this boundary, it is a mirror image of this. This is my original structure, and the one that I'm talking about here is the mirror image. Okay, so what will happen is, another boundary will appear which will undo this, and it will again bring the structure as same what it was here in this part of the crystal. So twin boundary, it is a 2D defect across which the structure is a mirror image, and the interesting part is they occur in pairs, so that the change brought about by one of them is undone by the other. So the change that was brought about by this, it was making a mirror image, then it was again making a mirror image. So whatever change was brought about by one was undone by two. Okay. So twin boundary, it is a planar defect, okay, which shows a displacement of atom by a stress that reorients the volume of the crystal. And this is bounded by a twin boundary. Just remember, twin boundary is a 2D defect across which your crystal structure is a mirror image. They occur in pairs so that the change brought about by the one is actually completely undone by the other, thus bringing the crystal to its original form. The next 2D defect that we would talk about is stacking fault. Again, very easy to remember because its name contains all the information. This happens by wrong stacking of the faulty stacking of the close packed layers. Okay, and how can it happen? You are growing a crystal, some jerk happens, or something happen, or by whatever factor, the stacking of the layer happens in a faulty manner. Okay, and they may also evolve from other defect, so that causes stacking fault. And what I want to say is, suppose your crystal structure was a CCP, so it had ABC, ABC, ABC kind of packing. What happens? Somewhere in the middle, you have ABC, AB, a C layer is missing, and you again have ABC, and then A continues to this. So what has actually happened is, in your CCP crystal structure, you got a region of HCP kind. So existence of HCP kind of region in CCP occurs. So what is this? This kind of defect is called the stacking fault. It happens by faulty stacking of the closed packed layer. Okay. Volume defects will not do too much about it. They are basically three-dimensional defects. They could be pores, they could be cracks, they could be foreign particles which have come in your polycrystalline or just a single crystal material. Okay. Sometimes they are added deliberately to strengthen the material or to get some other functionality. Okay. Now we have studied about 0D, 1D, 2D defects majorly. Okay. How can I study them? Once I have the defect, sometimes the defects are deliberately introduced because I want some particular property from it. For example, luminescence. Defect induced luminescence is a very important functionality. So how can I study when I introduce the defect, or they were existing already, I want to study them. So to study point defect, we can do conductivity study because you are creating vacancies, you are creating interstitial, and all of these are species that can move. I can do UV visible spectroscopy because the defects that are introducing will create another level in your energy diagram. So that can influence the absorption and excitation, absorption and emission characteristic of the material. Dielectric studies. So dielectric constant of the material can change. Dilatometric studies. Dilatometry is nothing but the studying the thermal expansion of the material. Okay. 1D and 2D defects can directly be seen if they are big enough. For example, your twin boundaries or stacking fault. Twin boundaries, you can see them by optical microscopy. If they are not very big, you can see them by electron microscopy. So microscopy images whatever is happening. So 1D and 2D defect can be visualized with the help of microscopic technique, SEM and PE, or also optical microscope. Color centered, by the name suggests they give color. You can study them by UV spectroscopic technique, primarily UV visible and X-ray spectroscopy. Okay, so just one example of how conductivity can be used to study the defects. Okay, let us take NaCl. Now your NaCl is a very poor ionic conductor. All right. Whatever conductivity will happen, it will happen because of the Schottky defect that are created in this. See, whenever you want your material to conduct, you have to have two things: species that can move and the pathways that are there for them to move. Then only the conduction will happen. In case of NaCl, the only thing, pure NaCl, the only thing that can provide the species that can move are Schottky defect. Why? Because Schottky defect will remove a pair of Na and Cl ion. So what will happen? It will be easier though there is a vacant spot. Okay. So the neighboring ion can hop into this. And when the charges hop, what is it? It's conduction, right? Now, how can I study the number of defects or the energetics of defect in case of NaCl? We are taking an example of technique that is ionic conductivity. Okay. Now, I also told you that defects can be they can also be classified by the way they are created. If they are already present in the material by whatever factor, let's say thermodynamic factor, they are called intrinsic defect. And if we deliberately dope something to create the defect, that is called an extrinsic defect. Okay. Now just keep that in mind. Now suppose I have NaCl. Okay. And I substitute some amount of calcium chloride in it. We'll talk more in detail about this kind of substitution in the next lecture. For now, you just assume, let's say 10 Na are replaced by 10 Ca. What will happen? Na had the charge of +1, Ca has the charge of +2. Always remember, electroneutrality has to be maintained. So what will happen is, one Ca, when it goes into the site of Na, it will knock off another Na. So that 1, 2 plus will replace 2 Na. Okay, so what will happen is, now because it can occupy only one side, right? It is knocking off 2 sodium. but it can occupy only one side. So it will create cation vacancies. Now I have two types of vacancies that can be created in sodium chloride by extrinsic factor, which I am doing by substituting calcium, by intrinsic factor, which are uh, controlled by thermodynamic reason. And also remember, I told you yesterday, Schottky defect, Frenkel defect, vacancies, interstitial. If you remember that energy graph, this is H, this is S, and this is G. When you increase the temperature, the number of defects will increase. It will move from this position to this position. Okay. So increasing the temperature will also increase your intrinsic defect. Okay. Now, when I measure conductivity, there are two types of conductivity. Of course, the substance doesn't know that it has two type of conductivity, but I know because I have doped something into it. So the vacancies that were created because of doping and are contributing to conductivity, that is called extrinsic conductivity, and conductivity that is due to contribution due to thermodynamically generated defect is intrinsic conductivity. Are we good? Now, what I do is I measure conductivity. So this is conductivity ka formula is given by this is your pre-exponential factor and this is your activation energy. That is energy required for the ions to move, irrespective of whether it was extrinsic or intrinsic. But the story how unfold is, suppose I took NaCl, this is my conductivity axis, this is my temperature axis. Of course, I'm plotting 1 by T because this, if you do log natural sigma, is log natural sigma naught, just forget this T for the moment, minus A upon KT. So I'm plotting this versus 1 by T. Okay, so my slope would be EA by K. Okay, now imagine I had NaCl doped with CaCl2. Now, when I'm at low temperature, which means 1 by T is high, the conductivity of the material will increase as I increase the temperature, but this conductivity is only due to the vacancies that were created by virtue of doping calcium, that is extrinsic vacancies. Because your intrinsic defects are very small, they become substantial only at high temperature. Okay. Now, so here, now because the slope represents the activation energy, this is the activation energy required only for the movement of charge. Because defects are already there, vacancies are already there. I have doped calcium, I have created defect. But at some point, what will happen is this conductivity will increase. So the slope has increased. Why? Because now your activation energy has got two components. One of it, which was instrumental here also, is your energy required for the mobility. But at higher temperature, you also have additional activation energy because now, as the temperature is rising, Schottky effects are being created. You need energy to move NaCl from their side. Okay, so that energy that we derived yesterday is EA by 2. Now, while this slope is actually Em by K, this particular slope is Em plus Ea by 2 upon K. Okay, so all this hope you have understood. Now we will do how do we do the calculation. So I don't know all this. I have only doped my material with calcium chloride. I acquire the conductivity values, plot this graph. I will get something like this. What I'll do is I'll determine the slope of this. This will give me the energy for the mobility, activation energy for the mobility. Then I'll take this slope. Now this slope is equal to Em plus Ef by 2. I know Em from this particular slope. I can calculate Ef. I can calculate the energy required for the creation of Schottky defect. If I get the energy required for the creation of Schottky defect, then by the formula that we derived yesterday, which is let's say n, which is the number of total lattice site, or also you can take it as the Avogadro's number, exponential minus EF by 2RT or KT, depending on you're taking one molecule or mole. I can calculate, sorry, this is NS, number of Schottky defect that are created is this. I know this, I know this, I know this, I know temperature. I have just calculated EF in the previous slide. I can calculate the number of or the concentration of thermodynamically generated defects. All right. This is how conductivity can be used to study point defects. I took just one example, one technique to demonstrate how we can study the defects. All right. With this, we close the defect part of the coursework. So we studied defects and why do they occur? How can we classify defect? How can we calculate the concentration of thermodynamically generated defect? We studied the classification of defect based on dimensionality and how to study these defects. Okay. With this, we end this lecture and we'll start the second part of today's lecture, that is solid solutions, but we'll take a break for 3-4 minutes. Thank you. Okay. So now this is a rather easier part of the coursework, and one of the most interesting thing also to understand solid solutions. Why, first of all, we need to study solid solutions. Okay. Uh, Basically, I was giving you the example of barium tightening and how the TC, the transition from ferroelectric to paraelectric can be controlled by substituting strontium in place of barium. So that is nothing but forming a solid solution of barium and strontium. So solid solution provide you a method by modifying the composition, and that modification of composition provides a unique way to control the structure and ultimately the properties. It's a very nice way of, or an easier way, and probably also the most logical way to tune the properties of the known material. And also, it also provides you the avenues to get better material. Suppose you want to improve on the functionality, uh, let's say ferroelectricity or ionic conductivity. So these are the material that give you some scope. Solid solution provides you a scope to improve the property of the material. Let's say zirconia, ZrO2. As such, ZrO2 exists at room temperature and it is monoclinic. But the same ZrO2, when you dope it with the Y3 plus or alkaline earth ion like calcium or barium, that creates vacancies and it makes it an excellent high temperature ionic conductor. And then it has many applications, for example, solid oxide fuel cells and then catalysis and so on. Ceria. Ceria as such also is a good ionic conductor at relatively lower temperature as compared to zirconia. But in Ceria also, if Ce4 plus is replaced by a trivalent ion, that creates vacancies and that it makes it a further better ionic conductor with many applications. Barium titanate, of course, I told you. We substitute barium titanate to, play with its electrical properties and we get modified ferroelectrics, relaxers, and, many other things that can be done by just making the solid solution with appropriate substituent. Okay. So what exactly are solid solution? Simple, light liquid solutions. They are the mixture of two solid, but not just the mixture. They are the same crystalline phase containing multi-elements. In terms of defects, solid solution are extrinsic defect. And many a time they are non-stoichiometric defect because they affect the stoichiometry of the, not many a time they affect the stoichiometry of the material because you're ultimately playing with the stoichiometry when you want to create a solid solution. So how to define solid solution? It is a crystalline phase having variable composition. Okay. So solution of two solid when they are present as single crystalline phase. So if I have a mixture of AO2 and BO2 like a bhel puri, that is a mixture. That is not a solid solution. But when they are present in a single crystalline phase, if I say I am mixing AO2 and BO2 and heating them, and they give me a solid, and that I am able to attribute to a solid where A and B are occupying similar lattice side, I call this a solid solution. That is A solid, B solid giving you AB solid. Now, how is it different from AB compound, AB solid? Your AB compound can have only 1:1 composition, A, B in 1:1 ratio. But when A and B can mix up to form solid solutions, then A and B can actually combine in various proportions. That is, your AB can have variable composition. Compound has only single fixed composition, but the solid solution can have variable composition, and that is how we differentiate a compound AB from a solid solution AB. Okay? So solid solution, as I just said, is a non-stoichiometric, is non-stoichiometry. You need not have a fixed stoichiometry for that. It can take variable amount of A and B, whereas the compound always has a fixed composition. For example, I can take alumina and chromia and mix it in any form I want. Let's say 100% alumina, of course, is alumina, then 90 alumina, 10 chromia, or 80 alumina, 20 chromia. Going on to the other end, 20 alumina, 80 chromia, and then 10 alumina and 90 chromium oxide. So it forms solid solution in the entire range. Okay. Similarly, your ceria and thoria also mix across the range from one end to other end, giving you a nice cubic type solid solution. Okay. In terms of structure, your solid solution could be similar to one of the end members or it could be different. That we have to study using X-ray diffraction. Okay. What are the different types of solid solution? First is substitutional. Very simple. I've just taken out A and put B in place of it. Nothing else has changed. Crystal structure remains same. That is called substitutional solid solution, where the guest atom or ion simply replaces your host atom and ion. Okay. For example, I mixed 80% of AO2, 20% of BO2, mixed them nicely, heated them at high temperature, and this is what you get. AO2 is the host, your B4 plus ion is the guest, and B4 plus directly replaces your A4 plus. Okay, now what are the conditions? And I'm talking right now only about the substitutional solid solution. The conditions that govern, of course, not substitutional, but in general, that govern the solid solution formation. What are the conditions that will say that solid solution formation will happen? Okay, like in liquid also sometimes we have immiscible liquids, right? The rules that govern them are called Hume-Rowe 3 rules. Most of the time, if you see, these are not just rules, these are very logical guidelines. They say that if your end members, let's say I'm putting AO2, I'm putting BO2 in AO2. My end members, that is A4 plus ion, when I take the example I took here, and B4 plus ion, have got similar sizes. They say end members should have similar sizes. Very logical thing. More the similarity, higher the solubility. The end members should have similar charge. Again, uh, that ensures the similarity between the guest and the host. If the charges are not similar, that doesn't mean the solid solution will not form, but the probability that they will form across the range from one end to other end will decrease. So what will happen is solubility might decrease because the other charge balancing mechanism will come into play. And the third rule is end members should be isostructural, similar structure. Again, this is not always necessary, but if they do, this ensures higher solubility. So for the complete solubility, for the complete solid solution formation, Hume-Rowe 3 rules state end members should have similar sizes, similar charge, and they should be isostructural. And as I said, these rules are simple guidelines. Now let me tell you one more thing. We can only talk about the logical things, and that is how we plan our experiment. Whether or not a solid solution will form, this has to be done to be seen experimentally. Okay? Of course, by experience, we can predict a lot of things. Like I have been working on rare earth oxide for so many years now. So I have a logical idea of whether these two things will mix or they will not mix. Or I can also probably predict the extent also because I've been working in this area for so long. But otherwise, to be very sure and to say that with some kind of authority, this has to be done experimentally. Okay. That was substitutional solid solution when your guest ion was simply replacing the host ion. Then there is another category of solid solution which we call as interstitial solid solution. Here, your guest will go and occupy interstices in your host crystal structure. It will not replace your host atom or ion. It will go and simply sit in the interstices that are available in that particular crystal structure. For example, we know a very famous reducing agent, palladium hydrogen, that is nothing but the interstitial solid solution of hydrogen in palladium. Hydrogen occupies interstitial site in face-centered cubic lattice of palladium. Similarly, the stainless steel that you use at home, that is nothing but carbon sitting in the interstices of FCC iron. Okay. So now in the previous slide or in the first slide where I give you this example, you would have noticed that I'm only talking about the cations replacing cation. So do the substitution solid solution with anions happen? They do happen, but they are rare. Why? For example, this solid solution happens. That gives NaCl 1 minus X BrX. They happen, but they're rare because there are not many anion pairs with similar sizes and bonding requirement. Okay. Having said that, solid solution with anions are also possible. Okay, now these substitution and interstitial, whatever I talked about, when your charges are similar, when your sizes are similar, and when they're isostructural, but more importantly, charge is similar. They are called simple solid solution. When the charge on your host and guest ion are different, that creates a total new story, and they are called complex solid solutions. Sorry. Yeah. So the complex solid solutions happen when the charges on your host and guest ion are different. Okay. Why? Because now the condition of maintaining electroneutrality comes into play. And how will that electroneutrality happen? Decides the mechanism of solid solution formation. Now let us take examples. Let's say your AX is the host. Okay. And your Bn plus is the guest. So what will happen? There are two conditions. The charge on the B is greater than A, or the charge on the A is greater than B. There are two conditions only that can happen. If they are similar, then we will go into the regime of simple solid solution. Now, when the charge on the A is greater than A, that implies that the charge on the guest is greater than host. Okay. Now, the charge on the guest is greater than host means you are actually increasing the positive charge in the material. Now you have to make it neutral, right? So how it can happen is either you decrease the positive charge in in your host. That means you are removing some of the host ion, and this is called cation deficient solid solution. Or you have increased the positive charge, consecutively increase the negative charge also. That is, you put in extra anions. That forms anion excess solid solution. Okay. Coming to the second side. The charge on your host is greater than the guest. So what will happen is now you have put in some guest in the place of A. The positive charge has reduced. Positive charge is reduced means now you need extra cations. You get cation excess solid solution. Or you also decrease some of the anions, leading to anion deficient solid solution. Okay. Now these four cases that we talked here, which are the consequence of maintaining electroneutrality, because of the fact that now charge imbalance has occurred because of dissimilar charges of A and B. Now these four are called solid solution mechanism, and they have to be measured experimentally. What do I mean when I say that? That is, suppose I am in this region when my charge on B is greater than charge on A, and I have formed a solid solution. I will not know what mechanism will it adopt, whether it will go to the cation deficient kind of mechanism or it will go into the anion excess kind of mechanism, because both of them are consequence of this one thing only. But I will have to study this experimentally, that actually what mechanism has been adopted. Having said that, this thing comes by experience also, but for somebody who's new, he has to determine it, establish it experimentally. Okay, so let us take example of all these four cases. Coming to the first, I am putting B in the A and my charge on B is greater now. Okay, so first example is calcium in NaCl. This is my guess. My guest has got higher charge than my host. Okay. So what will happen is, now each calcium that is entering in place of sodium is getting an extra positive charge, taking an extra positive charge with it. So it will either require introduction of an extra negative charge, which will form an ion excess, or a missing positive charge, cation deficient. So how do we write the nominal formula now? When I'm writing cation deficient, you simply write it as Na, Ca, and Cl. Okay. Now, for every, let's say I have put X calcium. For every Na, for every calcium that goes into NaCl, it is replacing one Na, right? But along with that, now I'm talking of cation deficient kind of mechanism. It is replacing one Na, and for the want of neutrality, it is knocking off one more Na. Ca2 plus is equal to 2 Na plus. Okay. That means how much Na is left now? 1 minus 2x. X calcium knocks off 2x Na. Na left is 1 minus 2x. Along with that, I have cation vacancy, which I denote by V, and X calcium will occupy the position of XNA and will create X vacancies. That is how I write the nominal formula of a cation deficient solid solution that has happened by doping calcium in NaCl. I'll repeat it again. Every calcium is equal to 2Na plus in terms of charge neutrality. Okay. That means if I put in one calcium, I have to either take out extra NAs or I have to put in extra chloride. Let us talk of extra Na. Extra Na means each calcium needs 2 Na. Okay. One of these Na site would be taken by calcium and one Na site would remain vacant. For every one calcium, I am removing 2 NAs. For every X calcium, I am removing 2X NAs. The number of NAs left is 1 minus 2X. X amount of vacancy is created, and this is how I write the nominal formula. Now, suppose I am talking of anion excess. Suppose what happens that it does not knock off extra Na, but it also takes in extra chlorine along with it. Then what will be the nominal formula? Nominal formula would be, let's say, write Na, Ca, Cl. Okay. XNA goes in because it is not knocking off any extra Na. It will remove only XNA because it has to take the place of Na. Na? So number of Na remaining are 1 minus X. X calcium go in, but now for every calcium, it needs an extra Cl, 1 plus X. So this is the nominal formula for anion excess solid solution in this case. Now, whether this would happen or this would happen, that has to be determined experimentally. I hope that is clear. Okay. Now, just an example. Okay, that was easy. NaCl, only 1 and 2 charge. How would you write the formula for the solid solution obtained by substituting Nb2O5 and Fe2O3? So in such cases, I would always suggest, first of all, this is, or you have to remember that this is again the case of the guest ion having higher charge than the host ion, right? This is your host and this is your guest. Okay, so that means I can either have cation vacant or anion excess solid solution. Okay, so how do I do that to equate? I generally teach students that you try to equate them. So when I try to equate the charges, obviously 3Nb5 is equal to 5 Fe3 plus 3 5 the 50, 5 3 the 15, right? Now you write your cation vacant. How will you write? Let's say you write Nb, okay, and sorry, Fe and Np, because I'm talking of Fe2O3 as a host and O3. We will not touch O because we are talking of cation vacancies here. Let me just put a place for vacancy also. Let us write this. Okay. Let's say I have put, now whenever I have these kind of valency 5 plus, there it was 1 and 2, so it was easy. Now I have 3 and 5. Okay. So let me talk in terms of the number of host stoichiometry that I take, because it becomes easy. I have substituted 3x of Nb. In terms of charge, 3 Nb are equal to 5 iron. That means if 3 Nb go into the lattice, 5 iron have to go out. If 3x Nb have to go to in the lattice, number of iron remaining are 1 minus 5x. So out of this 5x, that iron have been missing, 3 will be occupied by Nb, now 2 are remaining. So the vacancy is 2x. And this is the nominal formula for your cation excess solid solution that would be obtained by substituting Nb2O5 and Fe2O3. Okay. And how to write the anion excess? Again, when I'm talking of anion excess, I simply do not touch the cationic side. Okay. The only thing that I remember is that for in Fe2O3, okay, for every iron, I have 3 by 2 oxygen because it is FeO 1.5, right? In case of Nb2O5, for every Nb, I have 5 by 2 oxygen. So how many oxygen is extra? 1. For every Nb needs 5 by 2 minus 3 by 2, 5 minus 3 by 2, 2 by 2, 1 oxygen extra. Okay. So XNB would need X oxygen extra. So I have, let's say I've substituted XNB. Number of cations removed are X because I'm not touching the cationic lattice side now. This would be 3 plus, I hope I'm right. Okay. 3 plus 2X, sorry. 1.5 and this is 2.5. So for every NB, okay, because here it is a 2 also here, this is 3 plus 2x. Every NB needs 1 oxygen more than iron, X, but in the stoichiometric formula, because I'm not touching cationic side now, I have to take care of its coefficient, it is 2. So 2 into X, 3 plus 2x. And that is how I write the formula for the anion excess solid solution when I'm substituting this into this. Please go through it when you go back today. It's a little complicated example, but also very easy. Once you understand this, then you'll be able to write nominal formula for such solid solutions. Okay. So with this, I'll wind up here. And next class, we will do rest of this and the phase transitions. A little bit of phase transition. That is an interesting part. Okay. I'll wait for 2-3 minutes. So if there is any question, please ask me. Otherwise, we'll wind up the day. So if there are no questions, we'll wind up here. And I'll meet you on Friday. Friday we'll have a class at 4 o'clock only, at the usual time. So thank you very much.